We have seen what are the polar molecules and what are the non-polar molecules. The examples of non-polar molecules are hydrogen and oxygen, and the examples of polar molecules are water and HCl. Now let us see what will happen if an external field is applied on the positive and negative charges of a non-polar molecule. Okay, so first let us take the case of a non-polar molecule. So this is non-polar molecule. So if there is no electric field, there is no electric field, there is no effect on this molecule. The center of positive negative charges are at the same place and there is no effect of this electric field. Since there is no electric field, so it remains as same. But as soon as you apply an electric field which is non-zero, and what is the electric field? This side is plus, this side is minus. How can you tell that? Because negative charges are drifting on this side. So there is an induced dipole moment. So you can see the shape has been distorted. The negative charges has come to the left side while the positive charges has shifted towards the right side. The molecule is overall neutral, but there is a shift and the dipoles have been created by the non-zero electric field. So the non-polar molecule thus developed an induced dipole moment. So this is induced because it was not there, it was induced by the electric field and the shape distorts. The dielectric is said to be polarized by the external field. You saw that without any external field, there was no dipole and hence no dipole moment. It is polarized only on the application of electric field. This is for non-polar molecules like hydrogen and oxygen. Now let us take the case of polar molecules. What we saw is that HCl and water both have permanent dipole moment. So what happens in their case? It is little bit different. So for again see, even in absence of electric field there are dipoles exist. This is positive and negative charges are separated. This is positive and negative charges are separated. So there is a dipole, hence there is a dipole moment also. Since there is a dipole, there is a dipole moment. Both the charges are not at the same center. But problem is that since you know there are too many molecules in a conductor or in a dielectric, so there are too many molecules, so they are randomly oriented. One is in this direction, then one might be in this direction as well. So overall dipole moment is zero, net dipole moment is zero because of their random orientation. If you see them, so they are oriented randomly, see this one is has a direction, this is this direction, this one is this direction, this and this cancels out. Similarly if you see this is this one positive to negative, this is this direction and this is this direction, they cancels out. And again this have this direction, this have this direction. So overall they cancel each other, because they of their random direction. But as soon as you apply some external electric field, again positive on this left side, because you can see the negatives are on this left side and negative on the right side, so positives are aligning towards the right side. So even though this external electric field have not induced the dipole moment because it was already there, now if you see they have started aligning, that now you can see a shift, that this is in this direction, this is also similar direction. Now overall there is a direction that negative charges are toward left side while positive charges towards the right side. So they are aligning and this alignment is reducing the overall polarization in the material. So what happens here? Let me delete this one. Now, in absence of any external field, the different permanent dipoles are randomly oriented, that we have already seen, and due to thermal agitation. Why? Because of the temperature. Last year also we discussed that why molecules move. So why things are random? Because of temperature or thermal energy, temperature. So temperature is something which is making them random. So the total dipole moment is 0 because they were randomly oriented. There is a net dipole moment in the direction of electric field. When there is an electric field applied, you saw that there is a net dipole moment. All the negatively charged parts were aligning on the left, negative charges were aligning on the left, and positively charged sides were aligning on the right, that you saw. So dipole, so there is a net dipole moment in the direction of the field. So what was the field? This side was positive, this side was negative, and a net field was created. This was positive, so external field was in this direction, E naught. And if you see, there is also a field created inside, this positive and negative, so which will oppose the external electric field, but the dipole moment is in the same direction as the electric field. So dipole potential energy in external field tending to align the dipoles. So what is happening is that there is a potential energy of the dipoles which is trying to align these dipole in the external field, and the thermal energy. There is a comparison between two energies, this external electric field and temperature. So temperature is making them disordered while this external field is aligning them. Suppose this E naught external electric field or the dipole potential energy because of this is less and effect of temperature is high, then there will be a random system. As soon as this external electric field is this much that it overcomes the temperature, there is a net alignment, hence net dipole moment. Okay, temperature is disrupting the alignment while dipole potential energy is try to align. The dipole moment per unit volume is called polarization. See, this is an important factor. The dipole moment per unit volume. So again we are taking this dipole moment per unit volume. This is denoted by P and called polarization. What is polarization now? Polarization, when we align the dipoles, then per unit volume, the dipole moment, you know that every dipole has a dipole moment. P is equal to Q into 2A. This was the dipole moment. But when we add up the dipole moment per unit volume, this has been added for so many molecules, and when we take this per unit volume, that is called polarization and denoted by P. For many of the material, this is simply proportional to electric field. This is a very simple thing. If you increase E, the polarization will increase. This is a common case, as we discussed. As soon as you increase this electric field, there will be more and more alignment. If you increase this electric field, there will be more alignment. This is simple. Polarization increases as the electric field increases. What is this chi? This is a proportionality constant, and this is called electric susceptibility. This is electric susceptibility. So the polarization increases as you increase the electric field. That means higher the electric field, higher the alignment. Okay, higher the electric field, higher the alignment, and this chi E is electric susceptibility. This is a material property. Now let us come to the important question. that how does the polarized dielectric modify the original external field inside it. So there is an external field. So if the material has become polarized, then how will it affect the external field inside it?